Why is this not working? All right. Okay, so today's lecture, 25th lecture. And I wrestled with doing some like new topic that might be just interesting or doing a review. I think I settled, after conferring with the TAs, I settled on just doing a review of some of the material we talked about during the second half of this course. I actually kind of enjoyed teaching this course because it really let me sort of brush up on my PyTorch skills and like really hammer in a lot of machine learning concepts that I might not have been super comfortable with. So that's fun. And I mean, I wanted to actually like start maybe do a lecture or two on reinforcement learning, but then we would have to rush, and I'm sure there would be a non-negligible number of you that would like be upset by like just sort of introducing a topic and like, you know, that really isn't going to count for homeworks or anything. So I think what I'm going to do is I'm still going to do those lectures just for my own sake, and I'll probably put it on the ecemjr site later on. So feel free to check back periodically because I'll probably want to add more lectures just as a way to sort of, you know, brush up on concepts, review papers. But for today's lecture, I thought it would be nice to have just like an easy one, go over some problems that might be relevant to the midterm, might not be. At the very least, the concepts will be relevant to the midterm. And maybe field any questions you guys may have, and then, yeah, we can leave it at that, right? So, so today's a review lecture. I mean, as I posted the skill set and everything on the website, so the skill set is like everything from after the break on. I forgot exactly what that entails, but it entails deep neural nets. Let's see. We have a browser here. Yeah. Oh, geez. What happened to the site? Okay, something has happened to the site. I'm going to fix that. Oh, God. Every day. Every day. I got a feeling someone made a commit that like right as I was coming here, I was uploading to the site, and so, I noticed there was some extra garbage in my commit. So I got a feeling someone broke it. Okay, I'll fix that when I get back to my office. But yeah, so it's everything from deep neural nets on. Of course, that does not mean concepts from the first part of the course you could ignore. I mean, you still need to know what an activation function is, what different activation functions are. These things are cumulative, okay? So please don't lawyer me, okay? Please, like, you know, I'm telling you that the focus is going to be on the stuff that we learned after midterm 1, but concepts from before midterm 1 are still relevant, right? That's how knowledge works. So so the way I like to do review lectures is just, I mean, I could summarize things from previous lectures, but I mean, you have recordings of those lectures, so I don't really see the use of that. Instead, I think what I wanted you to do is just go over a couple questions. And if we have time, you guys could ask your own questions. But yeah, I'll just go over a couple sample questions. So first one, following two-layer network. Let's look at the two-layer model. If you remember, this is the two-layer model we discussed in the lecture. That was basically when we discussed the two half-moons graph. We were discussing why deep nets work, and it works because it combines a bunch of linear classifications, right? So instead of having a straight division between data points, you have multiple divisions between the data points. A second layer sums all those divisions together, and you could get something that's curved, right? So that was the point of. So that was the deep neural nets lecture. This was the code from deep neural nets, but unfortunately, it doesn't work. What's wrong with it? Please, nominate. We need a nonlinear activation function. Where do we need it?
Between the line x equals z equals, or else it's like you just
Yeah. Yep. We need a nonlinear activation function between these two. Between the calculation of these two layers, like so, right? So remember, we need nonlinearity in between all the layers. Why do we need nonlinearity? You said already, Dominique, but I'll if anyone else wants to repeat it, who is listening? Yeah, please. Yeah.
At that point, you might as well just keep on talking about the weight matrix.
Yeah. If you don't put ReLU in here, you basically have this matrix times this matrix gives you Z, right? X equals W1, W2. Z equals W1, W2, X, right? And in that case, there's functionally no difference between W1 times W2 and just a large matrix, a W, right? So because of that, because the network can't see that, you have to sort of find a way to differentiate between the layers. You have to tell the network, mathematically, these layers are separate. There has to be something that's separating these two layers so that the two weight matrices don't just combine on their own. So that's where you need something nonlinear, some nonlinear activation function. ReLU is a common one. What is the ReLU activation function? Who remembers what ReLU is? Yeah, please. Ben. Yeah, if x is positive, then you pass it right through. If x is negative, then you pass it through a 0, right? So you have that hinge right there, hinge graph. Yeah. So you need some sort of nonlinearity between the weight matrices to ensure that they don't get multiplied together. Any other examples of nonlinear activation? Any other examples of nonlinear activation functions? Please, yeah. Sigmoid, good. Any others? Yeah, please. Tan H, yep, tan H. What's the difference between tan H and sigmoid? Exactly. Sigmoid goes from 0 to 1. That has that S shape. It goes from 0 to 1. Tan H goes from -1 to 1, right? So tan H is basically for those times when you want to add in values, but you want to basically give the model, the model the opportunity to flip the signs. That's what tan H is good for. Sigmoid is when you want to add some values in, or you don't want to add some values in. Okay, so you only want to add in some of the values of the matrix. Does all that make sense? Okay. So yeah. So basically, when you have the two-layer model, you need to add some sort of nonlinearity somewhere between each matrix. You need to add some sort of linearity between each matrix. Yeah. Why is this not? I have something there between those two. Oh, I know why. There we go. Okay, so I'm gonna take a moment away from review. This is something interesting. Are computers linear? Are computers perfectly linear? If I give you integers probably, but an integer is a discrete value. Really, when we say linear, we want to know that something, you get a real and you get a real out, right? But a computer can't actually represent a real number, an exact real number, right? There is a precision, there is a bit off, right? Why? Yeah, please. Yeah. Yeah.
or whatever.
Yeah, exactly. Yeah. So I mean, the way computers work, we have the little floating points. We have this little formatting. This is for float 32. I know float 64 is standard now, but I don't have space. So we have a sign, we have a particular exponent, and we have a fraction, right? And so basically, this is taken from Wikipedia, by the way. So basically, we take this number. We have an integer here. We have a particular integer here. We have a sign here. And so this represents the number -1 to whatever this is. So if it's 0, then it's 1. If it's 1, then it's negative. Then we have 2 to the exponent, so 2 to whatever this integer is, times 1 point this fraction, right? So that works. I think there's an error somewhere here, isn't there? If this is a fraction, then this 0.1, and then this 2 to the exponent, 2 to the... Wait, it's not 1 point something, is it? We could figure this out. What was the floating point representation? It was the exponent, it was the significand, yep. What was the... Oh, man. I have to look at the... I was doing this off the top of my head. This is the... Oh, minus 127. That's the thing I missed, yeah. Yeah, I knew there was something. There was something there. Oops. You're right. Yeah, whoever said it was minus 127. There we go. Okay, so... e to the minus 27, 2 to the, yep. Okay, yeah, there we go. So, what does this mean? This means that computers cannot represent all real numbers, right? When we're trying to represent all the numbers, for instance, there is a tiny, tiny step. There's a tiny, tiny step that we can't get through. So for instance, float is 4 to float 32 here. 4 to float 32. If we want to actually go from -4 to the -38 to +4 to -38, you have sort of this continuous, you have these discontinuities, right? So what does that tell us? Well, there's a very well-known OpenAI blog post. I think it was published in 2017, I want to say, which actually identified this and actually said that, at the smallest scale, addition itself becomes nonlinear. So what they did is they basically trained a linear neural network, but had all the activation weights be very, very tiny, extremely tiny, so that you capture some of this nonlinearity. So the trick here is that you can't really do this with gradient descent. Gradient descent is all about sort of big swings, and sort of one thing you want to do is one thing that they wanted to do purposely here was make sure the gradients, like they wanted to make sure the actual weight value stayed around 0, very, very small, and just changed by extremely small, like 10 to the -38 increments, right? So what they did was they didn't use gradient descent. They used what's called evolution strategies. I don't know if this isn't something I commonly use, or have much experience with. But does anyone watch Veritasium? Veritasium is sort of like a science YouTuber. He has like a lot of like math and science videos. There's a great video that he did a couple, like 2 or 3 months ago on these sandwalkers. I don't know if you guys have seen those like those big sort of weird sculptures that look like basically beasts with lots of legs that have sails and basically walk around the sand. I think it's from. I think it's. I think the artist is in Norway or something. So Veritasium did a video on those and how he was describing how he designed those machines using evolution strategies. So evolution strategies in a very high level is basically the concept of basically starting from a bunch of different, basically it's an optimization algorithm where you have a bunch of different starting points and then you iterate on each of those starting points a little bit. And then the starting points that perform best according to some metrics, you let them have more children, and the starting points that perform less good, you let them have less children. And if you run this optimization algorithm enough, the optimal strategies will have more children, and then basically you get sort of an optimal pattern that way, right? That's sort of an alternative to gradient descent. There are all sorts of optimization strategies out there. But what was interesting was that OpenAI, you can't do this with a gradient descent, but they basically use evolution strategies to train a deep linear neural network on MNIST. And so if they just did that with gradient descent, they sort of got an accuracy of 94% and testing accuracy of 92%. But if they trained the linear network using, these evolution strategies while maintaining sort of very small swings in the weights, the same network achieved a 99% training and a 96.7 test accuracy. Okay, so all this is to say that it was a very interesting blog post. So the reference is there. Feel free to go into it. But all of this is to say that nonlinearity is everywhere. So in theory, you don't necessarily, you don't absolutely must have an activation function. It's possible to make something work without the activation explicitly because our world is nonlinear, but the activation function makes it much easier. And if I ask you on the exam what's missing, you still have to say activation function. Don't lure me. But I just thought this was an interesting blog post. This is one of my favorite blog posts. It's a good thing to bring up in interviews because a lot of people don't. It's a good conversation starter. All right. Okay. Anyway, so that's just a aside. That's just an aside. But yeah. So with the original concept, the major thing we were missing was activation functions, and you need activation functions to go in here. Is there anything else missing from this? When you would design sort of a network? You were designing, let's say this is for MNIST, sorry. Let's say this is for MNIST. I copied this for a different problem. But let's say this is for, we want to classify the MNIST digits. What else are we maybe missing in the network? Yeah. Oh, perfect. Okay, yeah. Oh, very, very completely correct answer, Patrick. Yeah. So if this is a classification network, you would probably want softmax towards the end there. Or it depends on if you're using as you said, it depends on if you're using the binary cross entropy loss function, which just takes in logits. Yeah. Either way. I wasn't even thinking about that, but good point. Okay, so let's just do some layer outputs. Problems. All right, so let's say we're given a 2D matrix image, I don't know. Well, yeah, let's say it's an image, a 2D matrix. And we have a particular kernel like so. We have these values: stride is 1, padding of 0, no bias, no activation function. What is the size of the output matrix? What's the size of the output matrix? We're applying the convolutional kernel to the 2D input matrix. So what's the size of the output matrix? All right. Well, I didn't write it down, so. Oh, it's fine. It's not hard. Any guesses? Daniel, you want? Yep, the size is 3 by 3. You want to guess what the actual output is? Let me just write it here. It's easy. So what's this value here? -4, good. What's this value? -9? Yeah, still -4. What's the value? -7, thank you. +4, yeah. And then -3, good. -3. -3, yeah. Yeah. Huh? Yeah, +3. Yeah. Yep, you're right. +3. Yep. Yeah, not too bad, right? I promise. I'm not here to trick you. Let's do another one. Max pooling. So I know you guys don't necessarily haven't seen this, but I think you'll probably figure out what the actual code is applying there. What's the size of the output? Or yeah, let's start off. What's the size of the output? How many rows, how many columns? Let's put it like that. What is this doing? Why is it like that? The window. Yeah, I just call it the window. Yeah. The kernel, yeah, but I always get confused because usually when you do convolutions, you say kernel. I always say window for, but yeah. Yeah, size of the window, right? The windows don't necessarily have to be square. So 2 rows by 1 column, right? And then we have a stride along each dimension of 2 rows or 2 positions by 1 position for the y, right? So how big would the output be in that case? What do you mean you need a different kernel?
Like our last kernel was 2 by 2. Could you
Yeah.
still use that same kernel because it was 2 by 1 window?
Well, you don't necessarily need to worry about the other kernel, right?
This is just the output size, not the actual output itself.
This is just the well, both. We want the output and the output itself, but this is separate from the previous one. So this input is not from the previous output. So yeah, so this is just separate from the previous convolution. No? You want to give it a shot?
Give what a shot?
Yeah, well, what size is the output? Let's start off with that.
What size? Okay, so we think it's going to be 2 rows by 4 columns.
Okay, sure. Why not? Okay, yes, I agree. I should say that. Yeah, I agree. So what would the actual values be?
4, 5, 6, 7.
Yeah.
8, 9, 6.
1896. Yeah, 1896. You know, if I was smart, I would have made that like 4, 5, 6, 7, 8, 9, 10, 11. But oh, foresight. Tricky thing. Okay, does that make sense? So not too bad, right? You know, there will be at least one question asking you what is the output of a particular layer, right? So just make sure you know. Oh, that makes sense? Yeah. Okay. All right. Let's see. Should we move on to the next one? Yeah. All right. Let's do a little bit of a harder one. I know you don't like this one, Daniel. We have to include a problem on parameter estimation. I know. It's okay. I promise it'll be all right. That's why we're doing it in practice now. I promise this was already in there before you told me you don't like it. So, but it's not too bad. Let's try it out. We want to estimate the parameters for a network, and I just created this network. It probably won't do anything very well in like real world, but you know, it's something. It's something. So we just want to estimate the number of parameters. For each layer, let's take it layer by layer. Let's determine the number of learnable parameters, and then we should probably determine the total number of parameters. Yeah, so I think that's fine. So the inputs. The input is a 3 by 4 by 4? Yeah. 3 by 4 by 4 image. All right, we can deal with this. Okay, so convolutional layer. Convolutional layer 1, right? Or is there only one in there? There's only one in there. So how many parameters are there in the convolutional layer? wait, is that? Oh, I'm not the convolution. I missed the batch normalization. Sorry. Batch normalization layer. And I think, did I say it here? Did I say batch norm 2D? No, I didn't. But that is a 2D batch normalization layer. Actually, maybe I'll just fix this. I can fix this right here. Batch normalization, 2D. There we go. Okay? So, how many parameters are there in a batch normalization layer? What do we remember batch normalization does? What's the new 2D mean? Yep. Well, there's 3 channels, right?
3 channels. Oh, 4 by. Okay.
4 by 4.
12 in total.
So how many? So let's say if there was only one channel, how many learnable parameters in a batch norm? Say that again. Right. So there is the here. Let me pull up. Yeah, it has 2 parameters. Yeah.
There's 2 of those for each channel.
Yep. There we go.
No, sorry. There's 1 of each for each channel.
Yep.
That would be 6.
Yes. Exactly. Yep. 6. Yeah. So there's 2. So with batch normalization, there's 2 parameters for each, let's say, layer, each channel. So the 2 parameters are the mean, which gets subtracted out there, and the variance, which sort of compresses or extends the compresses or spreads out the data points, right? So because there are 2 learnable parameters per 2D layer, and there are 3 channels, so that means there are 3 times 2 parameters. So this is equal to 6, right? Does that make sense? So batch normalization, remember, every batch normalization simply calculates. Batch normalization wants to basically center all the data points around 0, and it wants to get all the data points with roughly equal variances. Okay, because in practice, I'm not aware if there's a proof on this or not, but in practice, people notice that if you have data points with wildly different variances, it makes training harder. So if you have data distributions that are all roughly equal, training becomes easier. Does that make sense? Okay, so convolutional layer. So this is really the only tricky part. So how many learnable parameters are there in the convolutional layer? You got it, Dominic?
Yeah. I think it's going
Please.
to be, so like your C in, which I'm going to go with 7 channels going in the
Okay.
and then you have to multiply it by your height and width of your kernel.
Okay. Okay. It's 9 times. Wait, what? Oh yeah, it's yeah, 27 times. Yeah, 27 times 6, which is, tell me again. There you go, 162. All right. Well, yeah. So so easy way to remember this is, I mean, as Dominic most eloquently put it out, it was basically input channels. Each input channels is connected to each of the kernels, right? So we have the number of input channels, all the weights that connect to the kernels, then times the kernel size. So here we have a 3 by 3. It could be anything really we want, and then times the output channels. Does all that make sense? Yeah, please.
Can you explain why you multiply by the kernel size? You know, I had like, wouldn't it be like each convolution that goes to like one, that corresponds to one weight? So, I guess, actually, maybe I'm thinking about this wrong.
No, so tell me.
Because I'm thinking like, you only have, when you do multiple, you have a 3 by 3 kernel and a 4 by 4 matrix, you're only doing like 4, I guess, like operations there.
Right, right.
Isn't that the individual kernels are related?
So the kernels, yeah, the kernels have in terms also, right?
Okay,
Yeah. Yeah, here you got it. Yeah, yeah. No, the convolutional layer is the hardest one. In my opinion, it's the hardest one to gauge the number of parameters for. But honestly, if you remember this number of input channels times kernel size times output channels, you're pretty much good. And what are other layers? We shouldn't say die yet. Okay, so max pooling layer. Hopefully everyone got it. So max pooling layer. How many parameters in the pooling layer? Pooling layer. Yeah, please, Patrick. 0? Yeah, it's 0. Yeah, exactly. It's 0. Yeah, that's a trick. But the average pooling layer, how many parameters are in average pool? Also 0. Okay, fine. Yeah, he won't fall for it. Okay, good. All right. So and finally, what was the last one? Linear layer. Linear layer. Linear layer. How many parameters in a fully connected linear layer? Is there a it's not, okay, so if it's not stated explicitly, we're gonna assume that there is a bias term. Yeah, let's go with that. If it's not stated explicitly, there definitely is a bias term. So how many parameters in the linear layer? I mean, that depends on the size at the output at the pooling layer, right? Yeah. 2 by 2 by.
Yeah, 6 channels.
Is it 2 by 2? Wait, let's do this. I might be wrong in my notes also. So let's do this. Let me just do this real quick. So the batch norm. So we stay with each input channel. So then we have parameters. Have a number of parameters. What was the input? Oh, it was 4 by 4. So the batch normalization just doesn't change that. So we still get 4 by 4. Then the convolution, what was the convolution doing? Its kernel size is 3 by 3, stride of 1. So it's 3 by 3. It's getting, so what's the size of the output at the convolution? Yeah, 6 by 2 by 2. That's what I have, yeah. Yeah, 6 by 2 by 2. And then, what about at the output of the pooling layer? Yeah, 6 by 1 by 1. Okay, that's what I have. Okay. Yep. And then, so now, how many linear, so what's the input, how many parameters are at the input of the linear layer? 7? Wait, what? Oh, 70. Oh, got it. Yeah, yeah. Yeah, so output's 10 units. So how do you get 70? Yeah, yeah, exactly. We want the size of the output, the size of the input times the size of the output. So that's 6 times 10 plus the number of biases, which is, again, the size of the output. That's another 10. So then this equals 70. Right? Okay, good. So all this together, how many total parameters do we have? 238. Yeah, that's what I would get. That's what I think. Let's check it programmatically, just for our own sanity. So I just wrote a quick function. So again, just let's see, batch normalization, where the number of features is 3. Yep. 3 channels. 2D, where the number of input channels is 3, the number of output channels is 6, now kernel size is 3. Well, it's 3 by 3, but I don't have to do that. 2D. That's all makes sense. Then the pooling is kernel size of 2, stride of 2. Then the linear layer is 6 to 10. Input of 6, output of 10. And then forward, so we get a total number of parameters of 238. Yeah, that all works, right? Does that all that make sense to everyone? Yeah? Yeah, please.
Just kind of going back a little bit, but I was
Please.
wondering why is max pooling layer considered to have 0 parameters? Why isn't the batch normalization layer also considered to have 0 parameters? Aren't the the parameters you said are the mean and the standard deviation, but aren't those just kind of proxies of the layer that you can just derive without having to actually?
Those are actual model parameters. So the model itself sort of sets those parameters. So it's not just for each batch you derive the mean and variance, because it changes between batches, right? So it just the model, you give the model the ability itself to take the mean to basically shift the distributions as it sees fit. So I mean, I'm sort of, I mean, it's sort of my fault why you're thinking the way you do. You are thinking sort of correctly based off what I'm saying, that, you know, ideally the argument is that if all the distributions are equal, then it trains better. But in practice also, if you give the model sort of ability to shift the distributions around a bit, that also makes it train better also. So just being sort of stringent on a mean of 0 and variance of whatever isn't optimal either. It's basically you have to let the model sort of learn how each of the different features should be shifted around to combine well to get a particular output. But it does, I mean, in practice, it usually all sort of comes down to everything is around the same mean, but it's not perfectly the same. So that little bit of variation is kind of important in that sense. That's what people have learned, yeah. Yeah, so good. Any other questions? No? Okay, good. Yeah, don't be afraid of the parameter estimations. Let's see. All right, what else do we got? Network shaping. Oh, this one I wanted to go over. There's a question like this on the sample. There's going to be a question like this on the midterm. So I know that I just don't want anyone to sort of be scared off by it. But this this is a very classic machine learning sort of problem, interview problem, so probably a good idea to make sure you guys know it. Okay, so the goal of this problem is simply to basically replicate a particular output function given some network, okay? So the network that you're given is, in this case, the network that you are given is basically some layer. In our case, x is some real number. It's a single dimension input. W is a two hidden elements layer. W2 is one linear layer that has two elements. A is some bias, and then you pass it through an activation function, and then you pass it through another hidden layer, another linear layer, to get some particular output. Okay? So, yeah, that works. Yeah, you pass it through another linear layer that has a single output. That's what I wanted to say. You pass it through another linear layer that has a single output, and you get some particular output. Okay, so this linear layer has two outputs. This linear layer has one output. Doesn't really matter, but hopefully all that makes sense, right? This is literally just a linear layer that we've explored a whole bunch before. Okay, and the problem is saying that we want to basically we want this layer, this neural network, to replicate the function x plus 5. Okay? So, I mean, we've discussed training, we've discussed all sorts of optimization techniques, but in this particular case, we don't really need to train or optimize our stuff because we're humans. We have our massive pattern recognition brains, and we know that we could probably just assign some values to W0, W1, and A to get this function, right? So all this problem is asking, what are the values of W1, W0, and A that will give you the function x plus 5? And further, this sigma is not the sigmoid function. I know notation. This is like just how people do it. This sigma is actually is just sort of a generalized some nonlinear function, and we just give you that the sigma is ReLU. Okay. If we put ReLU in there, it also looks weird, so I just left it at sigma. Okay. Does all that make sense? Okay. So the question is, what should the values of W0, W1, and A be in order to get a function that is x plus 5? So helpful here to remember is that ReLU, the function for ReLU is simply equal to max of 0, 5. Okay? So, yeah, that works. Okay. So how should we approach this? Huh? Oh, that's just the standard form of ReLU. Well, I mean, ReLU just simply means that, oh, not 5x, or sorry. ReLU x, that's x, there we go. Thank you, Tom. Yeah. Max of 0, 5 wouldn't make sense. I don't know why. Okay, yeah. Okay. Oh Lord. So, how should we play around with some values?
I'd say we should first set x to 0.
set x to 0.
Oh yeah, because then you have to kind of solve for W1A being 5.
Oh,
No,
that's,
like, you just get rid of more of it. Extra bit like you're originally doing a scenario where x is 0.
okay. No, I like that. I haven't tried that before, but I like it. So let's assume x is let's like assume x is 0. X is 0. Then what do we want? We basically want f of x equal to w1 times, I'm going to write ReLU. I'm going to write ReLU. I know it looks weird, but we want ReLU A is equal to 5, right? And we know w1 is some sort of vector, like this. And we know A is also some sort of vector, I want to say. Yeah, A is also some sort of vector. Yeah. So, what can we do in this case? A is a two-dimensional vector.
Or we can just plug in a few values, like
Yeah. We plug in a few values. So what do you want to plug in, Dominic? Okay, 3, 2 for W1 and 1, 1 for A. So this would give us ReLU, so this would give us 1, 1 times 3, 2, and I think this is supposed to be transposed, 3, 2. So yeah, so then this would transpose, and that does give us 5. That does give us 5. Why not? Or there are a bunch of values that work, right? Why not? This also works. For instance, if we put 5 here, we put 5 here and 0 here, this would also work. 1, 1, right? I'm gonna leave this thread for a second. And instead of setting x to be equal to 0, let's do the other one. Let's set a to be equal to 0. Let's just simplify this a bunch. Let's get rid of a. Let's get rid of this plus 5. Let's get rid of the biases, right? We want W1 transpose 1 is equal to ReLU some matrix times x, like this. Oh. Some matrix and W1 transpose W1, W0. Okay? So here's what we want. We want this to be equal to, let's just say this one, we want this to be equal to x. Okay? So how do we do this? Let's say if x is equal to, if x is greater than 0, or greater than or equal to 0. Okay, if x is greater than or equal to 0, what do we want? We would like well, let's just for instance make W1 1, 1. What value of x would we need to put into W0 to get it to be equal to x if x is greater than 0? 1, 0, right? 1, 0 will work here. 1, 0. Because then in this case, we have ReLU of of x0 times something 1, 1. This is just equal to x, if x is positive, 0 times 1, 1 transpose, which is equal to x, right? If x is positive. If x is negative, though, if x is less than 0, no one can see this. Okay, I'm going to, if x is less than 0, what does ReLU of 10x be? ReLU of 10x would again be ReLU of x0. So then this would be equal to 0, 0, right? X disappears. How do we fix that? Is there a way to get it so that x doesn't disappear when you pass this matrix through this ReLU? Yeah, please, Ben. Yeah. Yeah, exactly. So if x is negative, then if we make this negative x, so if we make this negative 1, then this will be negative 1x, so then this will be negative x, which means x is negative, so it will be 0 up top here. But then on the bottom here, this would be the positive value of x, right? The magnitude of x, right? Which is close. But the unfortunate thing is that we're multiplying this by the 1, 1 transpose. 1, 1 transpose, which isn't quite x. This would still be the absolute value of x, right? So what can we do here to get this back to be negative? Yeah, for W1. We do 1, negative 1 for W1. So if we do 1, negative 1 for W1, then if x is negative, you pass it through to ReLU, it gives you the magnitude of x, then that multiplies by negative 1, which gives you x again. Does that make sense? You guys with me? So we're basically sort of negating this ReLU function, right? We're basically just altering the weights at x, altering the weights for the first layer, and then altering the weights for the second layer, and basically just getting around this ReLU function that only lets positive values pass through it. Make sense? Everyone with me? Okay, so we have a general format for what we like. You have a general format. So we want, actually, I should have erased that, but okay. F of x is equal to W1, 1, negative 1, times ReLU W0. That was 1, negative 1 also. 1, negative 1 times x, right? But now we have this bias term we want to get is equal to x plus 5. So we have, I gave you an extra constant term that's also a matrix called A. So what should this A be in order to make everything work out? Yeah. Yeah, same thing, but instead we put 5, negative 5 here. So what does this mean? It means that if x is greater than 0, greater than or equal to 0, then we have ReLU of all of this would be x is greater than or equal to 0, would be ReLU of all of this would be, this will be positive, this will be negative. So we would have x plus 5, the matrix x plus 5 times negative x minus 5. So then this would be negative. I mean, this will be negative. If x is positive, this would be positive. Therefore, this passes through, and we get 1, negative 1. And then we get, so then this doesn't pass through. This does pass through. Then we get x plus 5, 0 times 1, negative 1 transpose. Then we get x plus 5. And same thing with the reverse, except negative signs everywhere. Okay? Does that make sense to everyone? Okay. Sort of remember that general format. There's a very similar question in the sample. There's a very similar question going to be on the midterm. Okay? So just remember that general format. It's not too bad. But this is more a problem of sort of understanding the activation function and understanding how neural networks might get around the activation function. Okay? Yeah, please, Daniel.
Can we do everything all at once? Or we can do, say, if x plus 5 is bigger than 0, we have if x plus 5 is less than 0. Or we
Yeah.
have to do everything at one go. The problem is that.
Like, what do we have to show? Or
Like for the answer, like when we do like for x plus 5 bigger than 0, we have 1, 0, 1, 0, 5, 0.
yeah, that's okay.
Plus 5 smaller than 0, we have negative 1, 0,
Yeah.
Piecewise solution where you would have different.
Oh, could you just say for a piecewise solution? No, you have to actually just give the answers. Well, I mean, it asks you, what does it ask you? Problem, hand designing simple neural network, provide the appropriate weights. Yeah, okay, so it's asking you just to provide the weights. So you can't really put the conditional on the weights. You have to give the actual weights. Yeah, you have to actually give the weights, and then you just have to show why the weights are correct. Yeah. Oh, how nice that would be if you could just tell your computer if the input is between these values. I mean, well, you could actually do that in PyTorch. You definitely could put layers like that, but you can't here. Yeah. That's actually sort of the magic thing I always found about PyTorch is that it has, I mean, this was towards the beginning of the semester where I talked about how for every possible function, there's like a list of gradients that PyTorch has created. So like if you go through it, like you have things like max and ceil, and then you have like some really weird mathematical functions like gamma function stuff, and all of those gradients are in there. So you could use all those functions in your neural network. I mean, I don't ever see a neural network with a gamma function, but I've never seen it. But I just sort of want to do it just because it's there. Anyway, that's a tangent. Anyway, any other questions? Yeah, please.
What's like an acceptable way of being able to show why the answer is correct?
I mean, just basically what I did here. Just to say that if you could assume W1 is this, you could assume W2. You could assume W1 is this. You could assume W0 is this. You could assume A is this, and then you know if x is greater than 0, then if x is negative 0, then you could do out the whole computation and be like you still get a negative 5, x equals minus 5, and that's all that. That's all kosher. Yeah, you could show it either way.
I mean
Yeah.
here you say if x is bigger or equal to 0, but if
Yeah.
you didn't use 0,
That was essentially before we were going to 5.
yeah, like
Oh.
should be negative 5 there.
Hmm.
Because when it's x plus 5 bigger or bigger than 0.
Yes, but then you would just show 3 conditions basically. I think it still works with only 2 conditions. I don't think you necessarily need to. Let me think about this. Oh, because the ReLU function, you're saying if x plus 5 is positive, if x plus 5 is negative, and then you're saying, if x plus 5 is somewhere in between, or if,
Same because you put there when the x is bigger or equal to 0, should be x bigger or equal to negative 5. Then you ReLU give
if x is, so you would have to throw 3, right? You would have to, because if x is equal to 0 and if x is between 0 and negative 5, you would still have to show that it's still x plus 5. But that's easy to do, right? Because it would be a mix of the two things. Yeah. Yeah, that works. I think that works. Yeah. Okay. Okay. Oh, we're running out of time. Is there anything else? Okay. All right, let's just do a couple rapid fire transformers. I actually timed this out well for once. Okay. So three types of attention in the standard Vaswani transformer, Vaswani transformer architecture. What are three types of it? What are the three types of attention in the standard transformer model? The 2017 paper. I know there's a whole bunch, yeah. But yeah, in this 2017 paper. Who remembers the three types of attention? Please, Ben. Yeah, tell us. Regale us. Cross, self, yeah. Do you want help?
I'm blanking.
You're blanking? Dominique? Masked, yeah, masked, yeah. Yeah. Masked is, what does a masked attention do? Dominic, what does masked attention do?
Wasn't that, it was, like, that was in, like, the decoder. Like,
Yeah.
you would, like, feed the output of the encoder into the decoder.
Yeah.
I think it was. It was more so just so that, like, it wasn't training, like, like, you wouldn't, like, you couldn't cheat.
Yeah, basically it was just not letting you create attention values to tokens that are further up the line, that are in time steps that are forward from the token. So you've just masked half of the attention there. Yeah. Anyone know of any other types of attention other than those three in the original paper? Anyone could think of it? This is well beyond the midterm, but just like. I've heard interviewers ask this question, so I'm just wondering. Sparse attention is a good one. Sparse attention. Not every attention looks at every single, tries to relate the correlation between every single token. And in fact, doing that gets kind of expensive. If your context size, the context window size is like 2,000, 5,000 tokens, just calculating that enormous vector is kind of expensive. So there are other attention, a lot of the other attention mechanisms that came after this were sort of ways to compress the amount of values that you had to calculate. So one of those is a very well-known one is sparse attention, where it just looks at sort of how well this token relates to a few other tokens, to the most probable other tokens, not necessarily every single one. Yeah, anyway, that's a tangent. Okay, so besides missing the encoder, what is the difference between the standard transformer model and a decoder-only transformer model? I mean, obviously the decoder-only model doesn't have the encoder, but it doesn't have something else. What else is it missing? Yeah, Patrick. Yeah.
Well, if there's no encoder, then it can't do cross attention with the encoder's output.
Yep. Yep, decoder model has no cross attention because there's nothing to cross. Yeah, so you're just sort of, that whole area is just sort of passed through. What types of tasks are encoder-only transformer models good for? Yeah, please, Ami. Classification. Yeah, classification is a big one. Q&A is yes and no. Q&A, it depends on if you want to generate. It depends on if you want to. Well, let me ask you this: what tasks are decoder-only transformer models good for? Then you can finish it off. Yeah, generation. So ChatGPT, those are all decoder-only models because, you know, they want to generate text. So decoder-only models are good for generating text. Encoder-only models are good for classifying, analyzing text. And then with question and answer is a little bit of a strange task because it sort of falls in between of both. If you question and answer could mean you want to generate an answer, like you want a whole drawn out, like ChatGPT does. You want a whole drawn out, explanation. So that would you would be more inclined for a decoder only model, or it could also mean that the question, the answer is like 4 or like 10 or something. If it's some discrete value that you could put a classification layer on the output of, then an encoder model will probably work also. So there's a mix of those. I mean, I would probably accept either one. But yeah. Okay, so I think that covers it. We're out of time anyway. So any last minute questions? Yeah, please, Ben.
So like when you have generative is like decoder only, but there are like use cases for using like a generative model in order to classify. Like I could ask ChatGPT
Oh,
what
yeah.
it thinks about something.
Yeah.
So could that also apply to like the encoder? Could a like large enough encoder essentially function to generate as well?
Yes, I think you could make the argument that you could still generate text with encoder only models. Yeah, so it's a bit squishy. It is a bit squishy. Also, like not every AI model is only encoder or only decoder. A lot of models are mixed between the two. So a very famous one, T5, is both encoder and decoder, like is an encoder decoder model, and specifically because they wanted to build an AI model that could do all the tasks well. But the general rule of thumb is that if you want to generate text, it's harder to do it with an encoder-only model than a decoder-only model or an encoder-decoder model. So pick your battles is sort of the thing. But in theory, you could do either with any of them. It's squishy. Any other questions? Good question, though. Any other questions? All right, so the exam, the midterm 2 is on Thursday. I won't be here. I'm traveling, but your TAs, Niraj and Vishesh, would be here. Make sure you keep plugging away on your final projects. I think everything is working. Some hiccups with Kaggle, but we got it all sorted out, so that should be good. And I'll see you guys next week on Tuesday. All right, good luck, guys. Hey. Yeah, please.
So ultimately, it's about decode, like the vision, like
Well, in class we taught both the encoder and decoder models, right?
encoder is like the image one, like you have a big image and just like
Well, the encoder here, let me show you, is
because
why?
I'm quite confused about those three, like encoder, decoder, and attention. Like really, like I get encoders from previous slides. Like in previous lecture, we talked about the image one. Like you have a encoder that shrink down, and then you have a decoder that.
Yeah. But I mean, you've seen the encoder before.
I'm
One
just
sec.
don't know how it works.
Let me see if I find the lecture again.
No, I'm not pretty sure. But previously, when you were talking about image, you have an encoder, decoder model.
I think because the auto encoder is about lecture, it's mentioned in lecture 20. That one is talking about auto encoders.
I'm not pretty sure though.
It was in the transformer lecture. Okay, here we go.
But then auto encoder lecture generally give an example on it.
Yeah, there we go. So
Yeah.
this part is the encoder and this part is the decoder.
Oh.
So yeah, so you could have both of them together. You could have one or the other. That's fine. But you have both an encoder model that just takes in text and just turns it into something, same dimension as the input, but just something processed, process information, and then you have decoder model, which again takes the input but processes it and actually tries to give you text at the output. Does that make sense?
I see, but then how do encoder do classification? You just have something that has the same size as input.
Oh, then you just, if you want to do classification, if you have an encoder only model, then you just put like a linear layer here and just compress
Okay.
everything down to one.
So
Or
what's encoder really doing? Like what does encode mean? Encode, like
I mean, it's like encoder, it just means it's processing something, right? So it's like looking at the text being like, they're talking about men and like, running or something about athletics, it's just sort of trying to understand what the text is referring to and encode that in the matrix.
Okay, so actually based on the functionality we wanted to achieve, we just do some operation on the input that we
Yeah, exactly. Yeah. So I mean, okay, so that's the thing that was confusing you. Yeah, so if you wanted to use this for classification, you would still have to, oh, there we go. You would still have to put a layer here. Like you would have to put a linear layer here. Similar to, there's a linear layer and a softmax layer here, right, for like generating tokens. Like you would, if you have an encoder only model, you would still need a linear layer here to give you whatever you want. Like if it's a classification, you would want linear layer plus softmax. If it's, question and answer, like actual number, sort of you would want that
Linear
also.
layer.
Something, linear layer also, yeah.
And the decoder is, then what's a decoder? Why can't the decoder just like do some operation on the matrix and
Well, people have seen that the decoder does do that, right? People have seen that the decoder, you don't necessarily need an encoder, right? ChatGPT, they have decoder only models, but the decoder, but the two things together become relevant when you're trying to, for instance, like translation, right? When you want to translate like Chinese to English, right? You would put the Chinese text into the encoder, right? It would sort of process it and give you sort of the meaning in numbers of that text, and then you would use the decoder to generate the English text. So you would get sort of the meaning that you want from the English text. You would use the encoder to generate that meaning, and then you would feed it into the decoder, and the decoder would generate one word at a time what the English text should be. Or like question and answering, you could, if you want, you would have the encoder, like you would put the question into the encoder, and then you would use the decoder to generate the answer, right? So that you didn't absolutely need it? No, I mean, ChatGPT has shown us that you could get away a lot with just using the decoder, right?
Yeah.
But also, like there's a lot of research that shows that, having both together, especially when you're resource constrained, I mean, OpenAI isn't resource constrained, right? They could do trillions and trillions. You could really overcome any problem you have if you have just an insane amount of computing power with you, right? So so choosing a good architecture becomes less relevant when you have like billions of GPUs training your models. But if you don't have that, you have to be smart about choosing the right architecture. Then it could make sense to use the encoder and decoder. So that's why.
And then what is attention doing? What is attention? Why
Attention is just sort of relating, this token is related to this other token. And then we're just like going to combine or separate tokens that are related. So that's all attention is doing. Like if the boy who was very bright, like sat on the bench. Attention is just sort of trying to process the language to say, okay, the boy, I'm going to add in some information to mark that he's bright, that he's intelligent. So that's all attention is doing, is combining tokens and separating tokens.
So it like shows the relationship between each token?
Yeah.
Okay, so what does it do really specific, like in the matrix side? Like how do you do the operation? Like
It's just the query key values stuff.
Add something to the matrix? Like
Yeah. It's just the weights and the query key. Like it's just the.
You just change the number in the matrix somehow?
Yeah. It's just the weights of the matrix change, right? Because you multiply each of these things by weights, right? So when you have lots of weights in there, as you're training it, it just changes the weights, and then sort of based on the weights, things happen.
Okay. And self-attention is once related to itself?
Yeah, self-attention is just like when the query and key and values are all from the actual input.
So you're relating input with itself.
Yeah.
Like say there are 5 words in the input, and you're relating those 5 words with itself.
Yeah.
And cross attention is like when you're